This problem taken from the 1986 AP version C Electricity and Magnetism exam. It's problem number 2 from the year 1986. It's a problem that involves combination resistor circuits, RC circuits. In other words, circuits have resistors and capacitors. And then another final portion of this exam question involves circuits that incorporate resistors and inductors. So this provides good review for a lot of our units of study. So let's get into it. It shows that 5 resistors are connected to a 25 volt source, and the battery is an ideal battery, 0 internal resistance. So we can either call this V subscript B for V battery, or we can call it an EMF. Either way, 25 volts of potential difference. One of the 5 resistors is labeled as resistor R, and we need to find the current in that resistor. Okay, so let's just diagram this a little differently. I think this is the same thing as a 5 ohm resistor that then junctions into 2 paths. One path has resistor R of 10 ohms and a 30 ohm resistor connected in series. The other path has, well, the same equivalent resistance, just in the opposite order, 30 and 10. I find it a little easier to view the circuit in this form, and then I need to reduce that into something I can relate to a little better. Okay, well, I know the rules for series resistors. We just add their resistance together when in series. So I can reduce the circuit to a 5 ohm, a 40 ohm, and a 40 ohm. And now the two 40 ohm resistances are in parallel with each other. So let's number these. Step 1, step 2. Let's reduce it again. In step 3, we get a 5 ohm resistor in series with 20 ohms. Isn't that the deal of having 2 identical resistances in parallel have an equivalent value just equal to half of either one of their resistances? So finally, in step 4, we can say this whole circuit behaves as an equivalent resistance of 25 ohms. So let's apply Ohm's law. Well, this couldn't be any easier. When 25 volts is applied to 25 ohms, right, if I is equal to V over R, then there's just 1 amp flowing through the battery. And when 1 amp flows through 5 ohms of resistance, you get a voltage drop of 5 volts. So let's just assume that this part of the circuit was grounded. Then we know right here, at this point, V equals 0. And then right here, V equals 25. So if 1 amp flows through 5 ohms, we get a drop of 5 volts. So the electric potential here is 20 volts. And remember, back here, we're back to 0 volts. So the potential difference from point X to point Y, if I'm allowed to label these junctions, is a potential difference of 20 compared to 20 volts. And when 20 volts is applied across a path that has a total of 40 ohms of resistance, let's see, 20 volts divided by 40 ohms would give us 0.5 amps. And that makes sense, right? Since this path is just as much resistance as this path, the 1 amp should split up evenly into half an amp and half an amp. So the question is, what's the current through the resistor labeled as R? Well, the current through this one is the same as it is through this one, but that happens to be 0.5 amps. Not so bad. So now the problem changes, and they say a 10 microfarad capacitor is connected between points A and B. So let's draw that in. The capacitor connects points A and B. They tell us that the currents in the circuit and the charge on the capacitor soon reach constant values, implying we reach what we call the steady state. So initially, when that capacitor is first introduced to the circuit, it offers 0 resistance to the flow of electricity. And so the current that comes to this junction then reaches yet another junction, and all bets are off on the amounts of current that are flowing here and here. So that's why we're told that given some time, the currents level off, and in the steady state, the resistance to the flow of current of the inductor is, for all practical purposes, infinite. So at that point, no current flows to the capacitor, and so we just get back to a point that whatever current has taken this path past junction X has no option. If it's flowed through the 10 ohm resistor, it's that very same amount of current that's also flowing through the 30 ohm resistor, right? There's no bit of current that follows down that branch because in the steady state, the capacitor has infinite resistance. So you know what? I'm pretty sure that once we get to the steady state, this circuit behaves exactly the same as the circuit we solved earlier. What's the current in the resistor labeled as R? I have no doubt that that current is still 0.5 amps. Okay, what's the charge on the capacitor? Let's see. Charge on a capacitor. QVC. Charge is equal to capacitance times voltage. Now, let me show you a mistake. 10 microfarads. 10 times 10 to the negative 6 farads. That's our capacitance. Here comes the mistake. Then I need to multiply that capacitance times a voltage. I see a voltage, 25 volts. Wrong. No. The voltage here is the voltage across the capacitor. That's the potential difference from points A to B. So we need to multiply the capacitance times VAB. So let's see if we can figure that out. Again, we're going to assume that this part of the circuit is grounded. So that's 0 volts. That's 25 volts. This is still 1 amp. So point X is at an electric potential of 20 volts. And now half an amp is flowing through our 10 ohm resistor. Half an amp times 10 ohms, that's a drop of another 5 volts. So point A is at an electric potential of 15 volts. And by the way, just to make sure that's correct, if half an amp continued onward and flowed through our 30 ohm resistor, 0.5 times 30 gives us 15. So a voltage drop of 15 from 15 brings us down to 0 volts. Hey, I think we did this right. What's the electric potential at point B? Well, like we just said, over here, where another half an amp is flowing, that's going to create a voltage drop across the 30 ohm resistor of 15 volts. But the potential here was 20 volts, so 20 minus 15 gives us VB is equal to 5 volts. So the electric potential at point A is 15 volts. The electric potential at point B is 5 volts. So VAB is equal to 15 volt minus 5 is 10 volts. So the charge on the capacitor is 100 times 10 to the negative 6th, a farad times a volt. Well, a farad is a coulomb per volt. Multiply that times volts. There we have it. 100 times 10 to the negative 6 coulombs. Oh, probably better to call it 100 microcoulombs. Moving on, the capacitor is now replaced with an inductor, a 2 Henry inductor. And we'll assume that the inductor is made of magical wire that has no resistance. Okay, for the sake of argument. There's our inductor. Once again, the currents reach constant values. What's the current in the resistor labeled as R? And what's the current in the inductor? Okay, now this is tricky. Initially, when this inductor is first introduced to the circuit, that's when it offers infinite resistance. But when we reach a new steady state, the resistance of the inductor is for all practical purposes 0, meaning the inductor is just behaving like bare wire. Okay, so let's draw this out. If we had a 5 ohm resistor a 10 ohm resistor, a 30 ohm resistor, and then just bare wire, and another 30 ohm resistor, and another 10 ohm resistor. Yeah. In the steady state, the inductor might as well be bare wire. Not initially. Initially, the inductor might as well be an open switch offering infinite resistance. But in the steady state, the inductor just creates a short circuit between points A and B. So if we want, we can diagram the circuit like this. There's 5 ohms, and then that splits off to a 10 ohm and a 30 ohm resistor connected in parallel with each other, and then that's followed by a 30 ohm and a 10 ohm. These are all ohms, and then on we go, right? In other words, if you look at this part of the circuit, that's just a bunch of wire in sort of a, well, in sort of an I shape, but still just a bunch of wire. And if we look at this part of the circuit, it's just a bunch of wire. Okay, so let's see what we get here. That's the same as 5 ohms. And then what's the rule for resistors in parallel? 1 over R equivalent is 1 over R1 plus 1 over R2. Or that's the same thing as saying R equivalent is the product divided by the sum. So we get 10 times 30 divided by 10 plus 30, which would be 40. So we have 300 over 40. That's the same thing as 30 over 4. That's the same thing as 15, 7.5. Okay, so this is 5 ohms, 7.5 ohms, and then again another 7.5 ohms. So this ends up being the same thing as having 20 ohms of resistance for the whole circuit. And that's all connected to 25 volts of potential difference. So now the current that flows through the battery and through the 5 ohm resistor, given by Ohm's law, is 25 volts divided by 20 ohms, and this gives us 1.25 amps. So the 1.25 amps reaches a junction. 1.25 amps flows to this junction, and now it's going to split up. Some of it taking the path to the left, some of it taking the path to the right. Well, how about we say the current that flows here is X? Then wouldn't you expect the current that flows through the 10 ohm resistor is 3 times as great? If it's 1/3 of the resistance, it should be 3 times the current. So applying Kirchhoff's junction rule to this point, the current flowing in is 1.25 amps, and the current flowing out is a total of 3x plus x. So Kirchhoff's junction rule says 1.25 amps in is equal to 4x flowing out. So x is equal to 1.25. Let's see, what's an easier way to say 1.25? Could we call that 5/4? How's that? So x is equal to 5/4 divided by 4, or in other words, 5/16 of an amp. But that's the current through the 30 ohm resistor. We want the current that goes to the 10 ohm resistor, so it should be 3 times as much of that. So x should be equal to 15/16 of an amp, and it's good enough to refer to it as that, right? We'll call it I subscript 10 ohms is equal to 15/16 of an amp. If you want to grab a calculator and express that as a decimal, 15/16 is equal to 0.9375 amp. Okay, that took a little more work, and that's just our answer to part D. we still need to find the answer to part E, the amount of current in the inductor. Well, let's draw this out. So now we know the current flowing here through the 5 ohm resistor is 1.25 amps. The current flowing here is, well, let's just call it 15/16 of an amp. So the current flowing here is equal to 5/16 of an amp, right? Well, I think we can argue that those currents, if we look down here, those currents recombine, the 15/16 and the 5/16 recombine and flow here. 15/16 plus 5/16 is 20/16, but that's right back to that same 1.25 amps that was flowing through the 5 ohm resistor. And then it's going to split up again. And it's going to split up in the same ratio, except here we get the 15/16 on the right and the 5/16 on the left. Are you keeping up with my writing? Okay, so what's the amount of current flowing through the inductor? This isn't really bare wire. This is wire that's been wound around into a solenoid shape. So 15/16 of an amp flows here, but then here we've only got 5/16 of an amp flowing. So how much must have flowed this way? Well, the only way we can go from 15/16 down to 5/16 is if 10/16 of the current took this path. Oh, and by the way, if that 10/16 of an amp at this junction combines up with another 5/16, then we get, just as we thought, 15/16 flowing here. And now this 15/16 of an amp joins up with this 5/16 of an amp to give us a total of 20/16, but that's the same thing as 1.25 amps, and it all makes sense. So the amount of current through the inductor is 10/16 of an amp. If you'd rather state that as a decimal, 10/16 of an amp is 0.625 amps. Okay, so the only new information we had, if you want to summarize in this problem, is the behavior of an inductor when it reaches the steady state. And in the steady state, an inductor behaves as a short circuit.